to bring over this 1 nanocoulomb of charge. That's 10 to the negative 9 coulombs. Put them right here. And let's show the electric field. Yeah, there it goes. It's coming off in all directions. Now, I'm going to show the voltage that's around this thing. All right, now, some of you haven't been taught yet, but just from the lab, you might be able to gather this. What do you think the voltage lines are going to look like here? Or what's the voltage going to look like around this thing? It's actually going to be, it'll actually be nice concentric circular lines around there. Okay, now here's the question. It'll have a nice positive potential as we get closer here. What happens as we go out to infinity? What happens to the potential or the voltage? It goes to 0. Just kind of like, notice how these are, the electric field lines are starting to fade out. It's saying it's got a voltage of 4 volts right there. Let's go ahead and put the plot in. There's nice concentric circle. Let's move it in a little bit closer. Let's plot that one. There we go. Okay, and there's 7.9. See how the voltage is getting higher as we get closer. There it's 20. Let's put that one in. Okay, let's show the voltage resolution. There we go. And no, let's put it in high resolution. There we go. Ooh, nice high resolution. As you can see, the darker it is right. I'm supposed to use the gyro mouse. I'll use this. The darker it is right here, the higher the voltage. We come in. Now, I wish it wouldn't do that. That scares me every time that happens. All right, now, let's take a negative charge. Okay? Let's take a negative charge. Now, remember, voltage was supposed to stand forward and right here. There we go. All right. Now, the equation for voltage, V equals, oh, Naomi, you snuck in on me. I've got your quiz sitting right up here. All right. It is equal to V equals K, that little constant K, times Q divided by R. Okay? And Q is the charge that's nearby. Okay? It's the charge that's nearby. So I've got a question for you. We can add up the voltage of a bunch of charges. So if I put a negative charge somewhere on this screen, do you think the voltage can be 0 somewhere then? If we take the same charge and put it on there, I bet you we can. Yes, because if I add the two up, they would, if they're equidistant away, so let's put this negative charge right here. Ooh, look at that. Now where it's white, notice this voltage, and split the distance between the two, the voltage is 0. Notice the electric field is not 0. Two things happen. One key thing here. The voltage lines, let's go ahead and plot the voltage. Let's get it closer in here. Okay, let's plot this voltage line. Now, you probably can't see it too well, but here's kind of a nice place to do it right here. Notice the voltage lines are perpendicular to the electric field lines. Okay, here in static electrodynamics, or it can't be static electrodynamics. That makes no sense. In electrostatics, okay, because dynamics means it's moving. We'll get to that in chapter 20, the next chapter. But anyway, as you can see here, it's nice and perpendicular lines. Now, oh, don't do that. Okay, so here we go. Now let's get closer to the negative, and right in. Oh, there it went to 0. I won't be able to get it ever again. Oh, I'm going to try it one more time. I'm going to drive you crazy. One more time. There we go. That's pretty close. All right, right in there, real close to here, the voltage is 0, and we can kind of see that. Now, as I get close to that other negative charge over here, the voltage becomes negative. Okay? And so like the potential difference between this positive 24 and this negative 24 would be the voltage would be 48 volts. That's the potential difference between the two of them. Okay? All right. So I just wanted you to see that. That's, as you guys were, with your little thing, this is pretty much what you were doing. You were going around probing where the voltage was always the same, right? The voltmeter wanted to be 0, so that you found that electric field that is right there. Okay, that type of thing. All right. Okay, let me pass back these 2 quizzes. My intrepid students here that sneak in. All right, there you go. All right, now, sneaking in, wearing a Jayhawk sweater, 2 strikes. All right, anyway, that's all right. That's okay. Okay, now, so let's go ahead and get out of that, and let's go into today's lecture, shall we? Let's turn on the lights, and we will open today's lecture. Was there any problems on the homework from chapters 18? Okay, Catherine has a question. And I will be available from between after class and before you all go to the lab to answer any homework questions. If there's a bunch of you, we will probably go to find a place to be. Okay. Which question was it, Catherine? 52A. Okay. All right. What were your Q for the inside shell? What was it? Times 10 to the negative 6 coulombs. Okay. What's Q to the outside shell? Oh, plus 7.74 times 10 to the negative 6 coulombs. Okay, now what was the radius of your inner shell here? 0.0755 meters. Okay, and what was the radius of your outside shell? 1.85. I'm writing while I've actually today I sent Wiley Plus an email saying that this problem 52 is a great problem, but they screwed it up because they got 1.85 meters. Okay, it should be 0.185 so that you have a real problem. Because here's the deal. When you all did problem 52 on Wiley Plus, it was the same thing, or it was the same charge for both A and B. You didn't have to take the difference between the two. Because remember, and yeah, John's going, oh, okay, I thought so, but I wasn't sure. Yeah, you're right. You were right. Because we know that the E field, which is what we're trying to find, is equal to sigma K, the Q enclosed. That's the big part. The Q enclosed divided by the echo naught times the area. And really, since we're dealing with a shell, with a spherical shell, we got 4 pi r squared, which is nice for the area, for the surface area here. So we wind up with K Q enclosed basically over the radius of the point that we're trying to find out here. Okay, so for A and B both. Now, the other problem that you could have run into that could have driven you crazy for hours over the weekend would be if you tried to put a negative number in there. It asked for, here's the other thing. Yes, that's what it asked for. And the magnitude is just like the absolute value. Okay? Always positive. So I bet you did you put a negative in there? Yeah. Because it's a negative charge. You reread that and you go, oh, magnitude. You put in a positive charge, you're good. You're golden. Okay? All right. Yeah, that one, I like that problem because of, I like the problem in the book. I hate what Wiley Plus did with it. Because in the book, you had this concentric circles and you're trying to find the electric field here, electric field here, and of course the electric field in the middle is 0. But the key is, it's the charge enclosed, so therefore, since it's the charge enclosed, if it's inside a conducting sphere, it'll be 0. All right. Any other questions over that? Okay, there's a new homework. There's a new sheriff in town. New homework on the board, and it will be due Friday. I just have on there now, I don't know why I got into that Miss Crunchmeister mode of punishing students for turning in late homework when the whole idea of punishing students for late homework was because you've got to grade it. I don't have to grade this stuff. It's automatically graded. So I've taken all that off, but I have put a due date on there. In other words, if you don't get around to it till this weekend or something like that, no points will be taken off. All right? But I highly encourage you to do them between now and Wednesday because there's like 5 of them with an extra credit on there because it'll help you for the test. There's a lot of pressure on you for the test because you're going to be taking it with 2 other people, and so therefore you don't want to show up and be the only idiot, right? So you want to study a little bit, all right? And John's going to ask me, what's going to be on the test? No, sorry.
Equation sheet or?
Oh yeah, yeah. Oh, I forgot to tell you. Yeah, it's going to be open book. Okay, it's going to be open book. So you're going to sit there and you're going to talk about physics and you're going to do like 5 problems together. Okay, and I'll even tell you what the problems are going to be.
So we're not having a test today? Not until next Monday?
Not
Wednesday. Wednesday. Oh, you were expecting a test today?
Yeah.
Sorry to disappoint. Okay. At the end of each chapter, I won't tell you exactly the problems, but at the end of each chapter, they have these concept and calculations problems. I'm going to pull them right out of there. Okay? So if between the homework that you do and if you study this stuff, you should be ready. You should be good. Okay, good. I know he's going to ask. So in other words, we should be able to get out of here quickly. And the beauty for me is there's only going to be about 10 of these things I have to grade. How cool is that? So anyway, there you go. So breathe, relax. This is 8 weeks. We're filling a bucket with a fire hose here with this stuff. All right? And a lot's going to spill out, but I do want you to understand what's going on so that when you're taking your MDAT or whatever it's called, or your MCAT, what is it for the dental people?
But we don't have physics on it.
Oh, you don't have physics on there? Losers. Okay, well anyway, so no physics? What do they expect?
But they require us to take this.
Okay, good. Well, at least they require some. All right. The DAT, and I understand one is Friday. There's one Friday, and but some of you may not be taking that one. All right. Now, let's go back to where we were completely confused. Chapter 19 stuff. I will not be using the laser light show. Here we go. We found out that something that I'm going to go to my old friend, the parallel plate capacitor. So much can be learned from this guy. Okay? All right. I've got a positive charge right here. Okay? I got a positive charge right here. And he is going to accelerate, right? He's going to accelerate from here to here because the force pushing on him is going to go that way. Correct? All right. Now, the nice thing inside the parallel plate capacitor is that the force is equal to the charge Q, well actually, this charge here, times the electric field. Okay? Now then, not this Q, this Q. Okay? Times the electric field inside there. Now, this isn't a quiz question, but it's just throwing a question out there. In a parallel plate capacitor, does that electric field change as we go from one plate to another? No, it stays constant. The electric field stays constant. All right? Okay, and he's going to go. He's going to feel a force. So he's going to, and this charge isn't going to change. So therefore, inside a parallel plate capacitor, the work that it takes to move this charge from here to, say, from a point A to a point B, let's just draw some lines like this. This is from A to B. To go from this delta S, from this distance delta S from A to B, the work required to go from A to B is equal to force times delta S. Luckily, the force stays constant. Okay? That was the key for Chapter 6 when, in Physics 1, when you all took Physics 1. And the mechanical part of it, of energy, was that work was equal to force times distance as long as the force didn't change. If the force changes, we've got to do integral calculus on the thing to figure it out. Okay? All right, so we wind up with this work equals A times B. Okay? And let's just plug this in. So we get the work to go from A to B on that little charge in that parallel plate capacitor is equal to Q naught. We'll call this guy Q naught. Times echo naught times that delta S. Okay. Now, let's take this work from A to B and divide by that little point charge, Q naught. In other words, we're dividing by joules per coulomb. Anybody remember what we call a joules per coulomb? A volt, exactly. This is a volt. Now, engineers like to use the word voltage. Physicists and other scientists like to use the word potential. Okay? It's a potential difference. In fact, there's probably I got a question for you. After we looked at that thing, in this parallel plate capacitor, actually what I've done here is I've drawn two voltage lines, really, because they are perpendicular. They're perpendicular to the E field line, because when the E field lines look like this? Yeah. There's the E field lines, and they're perpendicular to them. So I've drawn some voltage lines. Now, the voltage line right here, is that potential or voltage going to be positive or negative, do you think? It's real close to the positive charge. So it will be positive because V equals KQ over R, the distance away. Okay? But what about the voltage line over here? What's it going to be? It'll be negative. So there's definitely a potential difference here. Okay? So since I've drawn a voltage, this is what I've got here. This is a volt equals echo naught, or the electric field times delta S. Okay? So now, you'll say, oh yeah! The work required to move that charge divided by the actual charge was equal to VA minus VB, which equals E naught times delta S, okay, times that distance. This is inside a parallel plate capacitor, okay? All right, now, let's flip-flop these around, and let's do this. Let's do VB minus VA. Uh-oh, what did we just do? Now what happens to this guy? If you flip something around with a minus sign, what happens to this term right here? It becomes negative, right? Becomes negative. Negative E naught delta S. And so this is actually delta V divided by delta S equals negative E naught. So in your book, it looks like this. It says the E field is equal to that negative potential difference, VB minus VA. Okay? All right. That was kind of tricky. So let's back up just a little bit. Let's back up just a little bit. One of my favorite types of problems is example 4. But this is towards the end of the chapter. This is kind of the big idea. But what I want you to know is, all right, positive work is done to move this electron, or this proton, from here to here. Positive work is done. Okay? But that proton loses energy. All right? But the proton is losing energy. All right? Just like if I held this marker up here, it's got a high gravitational potential energy, but when I drop it, it's going to lose gravitational potential energy, but it's going to gain kinetic energy. All right? So let's see how all that works. Now, the energy in the system, we have kinetic energy. We learned about that first semester. What else did we learn about? Yeah, oh. Yeah, that was everybody's favorite problem. The bowling ball rolling down the hill. Learned about that one? Any others? Yeah, gravitational potential energy. Any others? What? Yep. Boing. There you go. 1/2 kx squared. One other one. Now we're getting into the electric potential energy, which is also tied in here, plus the EPE QV. The electric potential energy, which is Q delta V. Either VA minus VB or VB minus VA. So let's take a look at what that looks like in an actual problem. It says a particle has a mass of 1.8 times 10 to the negative 5th kilograms. Okay? And a charge of 3.0 times 10 to the negative 5th coulombs. Let me just carry this over here so I can do this for you all. All right. Particle has a mass of 1.8 times 10 to the negative 5 kilograms. All right? And it has a positive charge of positive 3.0 times 10 to the negative 5 coulombs. All right? Now, it is released from point A. Here it is. Here it's sitting here at point A. Okay? It's released. And from rest, and it accelerates to a point B. Right here. Here's my new charge at this point, point B. All right. The only forces acting on the particle are the gravitational force and an electrostatic force. Neither is shown in the drawing. The electric potential at A is 25 greater than at B. Okay? So, this is like plus 25, and this could be like at 0, or something like that, or 50 and 25, or positive 12.5 and negative 12.5. Okay? The potential difference between these two is 25 volts. Okay? So delta V is equal to 25 positive volts. Right? Now, it says this. It says, what is the translational speed of the particle at point B? So in other words, it's sitting here at 0. Okay. This little problem, this is what we want to find out. We want to find out VB. Okay? It stayed horizontal the entire time. So therefore, No Y, no G, no gravitational potential energy. It's not talking about the spin or the rotation of this little particle, so what else can we throw out? We don't have to worry about gravity. What else can we throw out? This guy. And he's not attached to a spring, thank goodness. Okay? So all we have to worry about is this and this. And here's the key question. Is the electrical force that it's feeling, in other words, think about, let's try and get a picture of what's going on here. He's hanging out here with a bunch of positive charges, okay? They're like glued to something. They can't move, but he's allowed to move. So where does he want to go? Well, there's a bunch of negative charges over here, right? He's attracted to that. There's electric field lines, pushing him that way. All right, so he's going to take off that way. All right, and is that a conservative or non-conservative force? It's a conservative force. All right, so we don't have to, so it's a nice conservative force. And so therefore, since it's a conservative, since things are conserved, the energy at the beginning equals the energy at the end. So, in other words, E naught equals E final. By the time we hit chapter 6 of last semester, you probably got sick of me writing E naught equals E final all the time. But let's just go with what's his original. This guy's 0. And the only other thing he's got here is this Q times delta V. So we go, oh, okay. Well, this would be Q times the delta V is equal to the only other energy at the end is 1/2 mVb squared. Well, shoot. We figured this out pretty quick. The book took like 3 pages. Of course, they were doing all this explaining, though, too. Delta V divided by m equals Vb squared. Ta-da! And it turns out it's like, for this, plug in the numbers, it's like 9.1 meters per second. All right? So there's an application of it.
Why isn't it like Q delta V equals half of V squared plus?
Oh, okay. Catherine
Because I know like
cut through me. Yeah. All right. Okay. Here's the deal. Here's the deal. Let's draw it this way. Let's do it this way. Let's do this potential difference. Since I know the potential difference is 25 volts, I can just make up any 2 numbers that are separated by 25 and put them on there. Okay? So let's do it this way. Let's say that this is 12.5 and this is negative 12.5 volts. Then I combined all that in one step right here because of the delta V. If I just left it as QV, which is really what you're supposed to do. This is what the book did. They left it as QVA. So this would be Q times 12.5. That's on here. Here's what I'm doing. Let's do it this way. Here's Catherine's question. She goes, how did you do that? You're doing your algebra magic again. Yes, and I'm throwing out a key physical principle. So good question. So let's do this. So in other words, E naught is equal to just equal to Q times 12.5. Right? That's what E naught is equal to. Okay? Right at the beginning. E final is equal to is equal to 1/2 mvb squared plus q times negative 12.5. Right? So let's set these two equal to q times 12.5 equals 1/2 mvb squared minus q times 12.5. Add him to both sides. And I wind up with q times 25, which is my delta v, equals 1/2. Not quite yet. Oh, I'm adding 12.5 plus 12.5 q's. So it's 25 q's. Yeah, this is fraught with algebraic peril all over the place. You make little mistakes. So that's what we did. Okay? Good question. Nice. Good question. I've got to learn. You can't rush chapter 19. Even though it's only 5 sections, people who haven't seen it before, you can't just go, well, here it is. Anybody can figure this out. Well, I've had many years to figure it out. And I'm still learning new things all the time. Every time I read your chapter, I'm like, oh, yeah. Well, that makes sense now. Okay. So I got to keep that in mind, especially for an 8-week course. That's why tests are going to be group therapy. It'll be great. All right. Okay, now then. I think you all have a good idea. I could go through the derivations, but I don't want to do that. I just want to look at, I already went through one derivation here. Trying to think. Okay, here's the deal. Let's keep that particle that's moving in mind here. That one that's moving, so its positive work is being done to it. Okay, positive work is being done to it. Now, as that charge gets further and further away, in other words, let's say it's being pushed away, and there's not another. It's getting out to a potential here that's close to 0. Okay. As it gets further and further away, out at infinity, here's the way we physicists take care of this problem. We say at r equals infinity, then that's our reference point. Then the voltage out at infinity is 0. Okay? Then the voltage out at infinity is 0. And so here's really what we're doing all the time, is we're doing this. We're saying, okay, voltage is equal to Q, K, Q over R. Okay? And it depends on Q. Okay? Depends on Q and it depends on R. All right? So now, let's say I've got plus 4 microcoulombs right here. Okay? And let's take this distance at about 1.2 meters away. All right. Let's do it this way. I'm going to put my plus 4 charge right there. And here's my voltage. The y-axis is my voltage, and the x-axis is my radius. Okay? In other words, as I move in closer, what happens to the voltage? It's going to go up, right? And then as I get further away, it's going to go down to where all the way out at 0, it's going to equal infinity. Okay? What's that? Oh, it's a 1 over. It's a 1 over. It is an exponential. It's r to the negative 1. Right? Okay?
So, if by convention we assume that as r approaches infinity, b equals 0.
Right. That's the magic thing. That's the physicists have waved for hundreds of years and said, let's make this work. Let's set r equals at infinity, v is equal to 0. They do the same thing with gravitational potential energy, actually.
So no limits
No. Right. No, none of that. You'd do that in 250, but then the funny thing is, you know what they give for the 250 kids for tests? They give my tests. Okay? So you guys are getting the exact same course. You're just not having to, you're just less confused, I guess. I hope. But we'll see. All right, now, so let's take a look at this. What do you think this curve would look like? I'm going to put a negative 4 microcoulombs here. What does this one look like? Where this is v. So remember, this is positive, and this would be negative. So this is positive. V is my y-axis. R is my x-axis. What's this one going to look like? Okay, it's going to be in the 4th quad. In other words, as I'm coming back from here, as I get closer to this, I'm going to start at 0, and as I'm going to get closer like this, it's going to look like this. Exactly. That's the way that one looks. You're right. Okay? That's the way that potential looks. So it's big negative. All right? So with that in mind, here comes, we can also add potentials together. Okay? We can add potentials together, and we can figure out the total energy of 3 charges sitting together. Okay? What's the energy of that configuration or of charges together based on the electric potential energy would be Q times the voltage, or Q times the potential. That's there. So let's take a look at an example of this. Here we go. Let's say I've got plus 8 microcoulombs right here, and I've got negative 8.0 microcoulombs right here. And I've just on this line only, and let's say that the whole thing is 0.8 meters apart. Yeah. All right. Smart people. Right here at 0.4 meters, what do you think the total, the sum of the voltage is? Right there at that point. 0. Yep. It would be, the sum of the voltage would be 0, because it's going to equal K times 8.0 times 10 to the negative 6 coulombs over, from this point right here, be over 0.4 plus negative 8.0 times 10 to the negative 6 coulombs over 0.4. Well, that looks like 0 to me. Okay? I've just factored the K out as being both of them. Okay, now, what about right here? Is the voltage going to be, at this point right here, is it going to be, do you think the potential is going to be positive or negative there? It'll be positive. And what about over here? Is it going to be positive or negative? Negative. Right. It's going to be negative. And it's easy to figure out what the potential is. Because let's say this one is at 0.2 meters here, and it would be at 0.6 meters from this charge. And so the voltage there, you just add them up, would be K. I'm going to factor the K out because it shows up in both of them. Times 8.0 times 10 to the negative 6 coulombs divided by 0.2, because at this point it's 0.2 away, meters, plus negative 0.80 times 10 to the negative 6 divided by 0.6 meters. The magnitude of this one's not as strong because we're dividing by a bigger number. So the magnitude is not as strong, so it's definitely going to turn out to be positive. Okay.
Is that 0.6 or minus 6?
That's, you can't tell? It'd be 0.6. There you go. 0.6 meters. How could you possibly have done this in Royal Hall when you sat in the back there? Yeah, this is a much better scenario. Okay. All right. So here's the electric potential. Now, here we go. Let's do quiz question number 1. I think you guys are ready. You guys are ready. And I'm going to give you time to do it. And I'm going to go fancy. Watch this. Watch this. I'm going to go fancy with this. Did that turn on? Okay. Then we'll lower this. You guys are going, uh-oh, what's he doing? Killing time. So here we go. Now, here's your quiz. Watch this. You can't see that at all, can you? Zoom in. Oh, what a maroon! You can't do that. Is that one working? That's a little better. Can we see it? What if I turn off all the lights so that you can't write? Does that work? Ooh, can you see the right? Pretty good? Okay, that works pretty good. All right, here's the quiz. Quiz number 1. All right, it says figure shows 4 arrangements of 2 charges. Okay. In each arrangement, consider the electric potential energy, electric potential that the charges produce at the point P. Okay, so this is a positive 2Q. This would be negative Q, and this is 2 distance away, and this is 1 distance away. All right. In other words, what we want to do is rank the values of the potential in descending order. In other words, you're going to take the sums of this minus this and see how big that's going to be. And you're going to this and this and this and this and this and this. And you're going to see which one. Now, you're going to rank them in descending order. Now, just to kind of help you out here a little bit, Sesame Street, one of these things is not like the other. Well, actually, 2 of these things are just like the other. Which 2 problems are exactly the same? A and D or B and C? A and B. They're the exact same thing. Okay? So, what I'm telling you is, don't sit there and kill yourself with a bunch of trying to do Pythagorean theorem, finding the potential along here. This is nice straight lines. Okay? It's this V equals KQ over R. V equals KQ over R. Ready, set, go. John, can you see? And David and Cozy, can you all see? Okay. Seeing this thing or seeing the right?
Seeing the graph.
Oh. Okay. Zoom in more? Okay. If it's not going to work, we're going to just fail you guys and move on. Okay, I'm going to zoom out just a little bit. There. How's that? Is that better? It would have taken less time just to draw the damn things, but that's okay. Darn thing. Sorry. We're going out to millions of Americans every day. They can't wait for the next installment of Physics 220 from UMKC. Is this showing up on the movie, actually? It is? All right. Too fatty. That's good.
Can you turn on the lights back here?
Mm-hmm. Sorry, David. No, I can't. There we go. All right. What does it say? Descending order. Yeah, the largest one first. Which one of these configurations has the largest potential? Which one has the smallest? And two of them are the same. Okay. We got it? Good? If not, you can answer it at the end. You got the configuration. I can't stand it any longer. Just by looking at this, which one should be the biggest? Which one? Why? Most charge, closest to it. Right? Most charge, closest to it. All right? What if it was a negative 2 and a positive Q here? If it was just saying the magnitude of the potential, then that would still be that one. It would just be a negative. It would just be a bigger negative. Okay. All right. So yeah. Okay. So there's part of the answer right there is. All right. So we'll go ahead and kill this. And we'll turn that in because I've got one more little quiz question. Hopefully we'll get to it by the end of the hour. I think we will. All right, now let's go back. So you understand, I'm not going to do all the examples. I was going to lay out the examples, but I do need to do one example. I do it every semester. It's kind of like, when Grandpa's got to read The Night Before Christmas or something like that. And every semester it's a small disaster, but not this semester. It's going to work. I'm going to do the example. They have in the book. Basically what they want to do is they want to find out how much energy. Here's their question. The question is, it's example number 8. And they want to know this. They've got 3 point charges. Initially they're infinitely far apart. Okay? So if they're infinitely far apart, what's their potential? 0. Right. They're all starting out at 0 potential. All right? They are then brought together and placed at the corners of an equilateral triangle. Each side of the triangle has a length of 0.5 meters. Determine the electric potential energy of the triangular group. Okay? In other words, determine the amount by which the electric potential energy of the group differs from that of the 3 charges in their initial infinitely spread about configuration. Okay, so their initial potential energy, if their voltage is 0, QV is electric potential energy, so what is their initial energy? 0. And you can also lose energy, go negative or positive. So here's the deal. We've got 3 charges, and we're going to put them, we're going to paste them, see how much energy it takes to paste them on this equilateral triangle. All right? And the charges are thus. 5.0 microcoulombs, positive 6.0 microcoulombs, and negative 2.0 microcoulombs. Those are the charges that I'm going to paste on the corners of this equilateral triangle. All right? Here's the idea behind this. What we're going to do is we're going to put one charge up here. How much energy does it take to take this triangle out to infinity and attach it to one of the things? How much energy does that take, theoretically? None. I'm just going to pick one of the initial ones. Okay? So the initial one has the amount of energy I used is 0. So let's just start with this 5. Let's just put the 5.0 right here. Microcoulomb charge right here. All right? Now, this is going to cause a problem. Well, not a problem, but what's he doing? At this point here, there's a voltage, right? And at this point here, there's a voltage that in other words, there's a potential coming out from him, right? Because he's got the electric field is coming out this way and it's coming out that way, and there's a potential here. Is it positive or negative, do you think? the potential P, would be positive. And so the V right here is equal to K times 5.0 times 10 to the negative 6 coulombs divided by 0.5. That's the voltage right there. All right? And it's the same at both places. We got V here and V here. We'll call this V1 for right now. All right? So now, what we're going to do is we're going to take, well, let's take the negative 2 Coulomb charge. And let's bring him up to here. Okay? So now let's take this. So we got the plus 5. And now we're going to bring the negative 2 to right here. That took some energy. Actually, that little negative 2 Coulomb charge lost energy because he's going, ooh, positive charge. I'm going to run towards him. So he's running downhill just like the ball does. So he loses electric potential energy. All right? And here's how it works. He's going to lose QV. The EPE is going to equal Q times V, where Q is him, is the negative 2. Okay? So far, the electric potential energy that we've used so far is going to equal negative 2 times 10 to the negative 6 times V1. Okay? Times V1. Did I do it in the opposite order of the book? I probably did. I did. So I don't know what that number is. Here's V1 right here. Yeah. Oh, I know. It's 0.4. I bet. I'll bet money. Or is it 0.2? What'd you get? Okay. Don't worry about it. That's what the electric potential energy is going to be right now. Oh! But wait a second. Now I've got plus 5. And now I've got negative 2. So now I've got this new potential here at this point, right? That's being caused by this guy. There's a potential being caused by him. Well, actually, the electric field lines are coming into him. And there's a potential being caused, a positive potential being caused by him. So V2 actually equals K times the 5 times 10 to the negative 6 coulombs divided by 0.5, because it's an equilateral triangle, plus a negative 2.0 times 10 to the negative 6 coulombs. How are you going to see that? I don't know. Divided by 0.5. That's the new V2. Okay? So the energy that it's going to take to bring up the 6 Coulomb charge, I've already dealt with him. I got to bring up the 6 Coulomb charge and put him right here. And plop. Put him right there. Okay? This is my 6.0 times 10 to the negative 6 coulombs. All right? So I'm going to put right there. That energy, I'll call it electric potential energy 2, is equal to 6.0 times 10 to the negative 6 coulombs times V2, which V2 is all that up there. And so the total energy to build this little triangle, the total electric and the electric potential energy of this thing is EP1 plus EP2. I figured out how I can do that problem. That went very well this time. Don't put any numbers in, then I'm good. So when I start putting numbers in, I get all discombobulated. because EP0 is equal to 0, just by arbitrarily saying, okay, we'll just start at this point. Okay? All right, now, oh boy, when your brain is completely shot, I'm going to introduce one more little concept here, and it's very important. It's very important because we've got to have quiz question 2 coming up. Except I think we'll just end with quiz 1 today. But we've got about 8 minutes. And like I said, I'll be in my office until you guys have to go to lab. All right, now, here's the deal. We're going to look at equal potential surfaces. Okay? Now, let's say I got a nice positive Q charge here. It's got electric. There's my electric field coming off of it. Okay? Now, we already saw by that one at the beginning of the class, here's my potential. Here's my line, potential line through there. Okay? Here's another one. It's going to be a little bit higher. All right? Now, let's say I want to move a particle from here to here along a potential field line. Okay? Okay? The electric force that this little charge would feel, say I got some Q naught out here, the electric force that this charge would feel, first of all, if it's a positive charge, it's feeling a force that's pushing it out, right? But the work done by that electric force to take it from here to here is equal to 0. The work to go from A to B in this case is 0. Okay? In other words, the work done, the net electrical force, does no work as the charge moves on an equal potential surface. Okay? So the amount of work done to go from A to B to C to D just to go around in that circle is 0. No work required. It's just like moving along. It's just like how much work does it take, how much work does gravity do as I move this thing from here to over here? How much work did gravity do? None. All right? It's just the same idea. All right? Okay, but if we want to go to E, the work to go from A to E, there is actually work that takes place. Okay? There's actual work that takes place there. All right? So here's this deal. Let's just see if you can do this. Here goes quiz question number 2. Let's just see if we can pull this off based on what you know right now. Just based on that 30 seconds of instruction. Here you go. You guys are troopers. You can do it. I know you can. All right. You're going to draw 2 potential. Here's 2 electric potential lines right here. Okay. And this is point C. This is point B. And this is point A. All right. Now, I've got electric field lines look like this. Why I missed A, I don't know. So I'm going to move it. There we go. I got electric field lines that look like that. Okay? And it says here, the drawing shows a cross-sectional view of 2 spherical equal potential surfaces and 2 electric field lines that are perpendicular to these surfaces. Okay, I've done that. When an electron moves from A to B, when an electron moves from A to B, against the electric field, okay, the electric force does 3.2 times 10 to the negative 19 joules of work. Okay, so the work from A to B on an electron is equal to positive 3.2 times 10 to the negative 19 joules. That's the work done on an electron to move it from A to B. That makes sense, right? Does it make sense? Because what kind of charges are down here? Negative charges. So where does that electron want to go? That way. So yeah, the electron is going to want to go this because they've got a bunch of negative charges down here. So the electron that's sitting here at A, he's going to go flying to B, right? He's going to lose energy, but the electric field, the work done by the electric force, is going to be positive. All right? Just like the work done by gravity when I drop my pen goes down. All right, so now you guys are going, hey, guy, it's 1:12. We're out of here at 1:15. What's the quiz? What's the question? Here he goes. What are the electropotential? What is the difference between, here's the question, what's VB minus VA? Okay? And remember this, Q naught equals negative 1.6 times 10 to the negative 19. All right, coulombs. And also know this, that VB minus VA equals the negative work, AB, divided by Q naught. What's VB minus VA? What's VB minus VC? And what's VC minus VA? Dun, 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 dun. They work it out kind of nice for us because that 10 to the negative 19, you don't need a calculator. Because the 10 to the negative 19s cancel. So basically you're talking, the work was 3.2 joules and you got a charge of 1.6 type thing. So it works out nice. Okay, yeah, that should, we got through. I knew I wouldn't get the capacitors today, but that's okay. There will be no new information. We can go to commercial now. Okay, so we can shut it down.